Kia ora and welcome to the screencast for Workshop 9. So this is the last week on classification, and we'll be looking at classifiers which you would have seen before, but perhaps in a different context. So we're looking at k-nearest neighbours, which you've seen in the imputation context for numeric variables. We're going to be using it in the classification context. Trees and forests, so you've seen those in the regression context, and neural networks, which you've also seen in the regression context. And we'll be using the tidy models frameworks for fitting and estimating our classes. So we're going to look at two data sets. The first we're going to look at is the GLASS data from earlier. So I'm going to start by running this first code block, which reads in the data, loads our packages, and sets things up. And we're going to be fitting a range of models to these data, and we're going to be using tidy models for it. And so we'll just go ahead and do so. So we're going to have a k-nearest neighbour model. Okay, mode is classification. Okay, and then we could fit our type in terms of everything with our training data. Right, so there's the nearest neighbour function. I think I might have spelt that wrong, have I? Let's have a look here. Nearest neighbour, yes, we have the American spelling. There we go. And then a classification tree. We might reduce the number of size of each node for that one because we don't have a huge number of observations. Okay, a forest. We'll perhaps use random forest engine. And neural net. Maybe we want to try to play around with the number of hidden units. Let's try 5. And we'll just use a bunch of epochs just to make sure that we converge. Okay, we could check convergence. And that's converged, so that's okay. Okay, and obviously there's some tuning to be done here, but first we're going to have to assess performance. And so we could just take each of our models in turn and augment with the new data from glass.test and then compute the accuracy. Okay, so there it is for k-nearest neighbours, and we could do it for the others as well, right? Okay, so here they all are here, and we can see that k-nearest neighbours and the random forest are doing best. But what I notice here is there's quite a bit of sort of boilerplate, isn't it? I've ran fit 4 times. I've run augment 4 times, I've run accuracy 4 times, and the formulation is identical in each case. Okay, so one thing that we might want to explore is how can we make this more efficient code-wise. So it won't be more efficient in terms of the running time on the computer necessarily. In fact, it probably won't be, but it'll mean we've got less typing. We just really copied and pasted here, but every time you copy and paste, there's the opportunity for you to mess something up. So how could we do this in a way that is perhaps a little bit more efficient? Well, one way to do it is to create a list. So we could go, our models are going to be a list of a nearest neighbor, a decision tree. So perhaps I'll put this down the bottom. A random forest. And an MLP, or a neural net array. Okay, so if I have a look at models, then I've got a list of those model specifications. And now that we have that list, we can apply the fit routine to all of the models in sequence. And so we do that using the map function. So some of you may have heard of map before, and essentially it's a way of iteration. It's applying the same function to each member of that list. So we want to take our models, pass it into map, apply the fit function with type equals dot and glass, and our data equals glass train. And when we do that, we can see that we have all of our fitted models. Now the disadvantage of this setup is that we're now don't know which one's which. I mean, we can kind of figure it out from the call, right? We've got KKNN, so that must be a nearest neighbor model. This looks like it's a regression tree. This is a random forest, and this is a neural net. But we can name the objects in the list, right? So we could have done KNN, RP, RF, and NN. Right, and then when I run my fitted models, they're labeled, right? So I've got KNN, RP, RF, and NN. So now that I've got my fitted models, right, all of this code down here can just be done by going fitted models, augment. So we've got a map with augment, new data, use glass.train test, and then right, so that will give us 4 data frames. We could then bind those data frames together, and there's specific functions for doing so. So if we just run bind rows, then we get them all together, and if we specify that the ID is going to be model, then it will add a column with the model type. So for each prediction, we have the predicted class as well as the predicted probabilities of each of the classes for the KNN model, and then again further down for the RP model, and so on and so forth, right? And for the NN model. And now that they're all bound up into a data frame, we could then, so this would be our glass predictions, right? We could then group by our model and work out the accuracy in one step. So the truth is going to be the type and the estimate will be our, right? And we get a nice data frame of the same results. We could also work out the confusion matrix. I seem to remember that on a grouped data frame, this will work as well. Let's see. It instead produces what's called a list col of our confusion matrix, which we will then have to we can, if we look at the help for confusion matrix, we can see that there's a tidy method. So we can use a tidy method. So we need to apply tidy to this column. And we're going to do that using a map because it's a list. All right, so for each entry in that list, we're going to apply the tidy function. So we need to iterate over the list and apply the tidy function to it. And so we're going to do a mutate to create a new column, which is going to be our tidied confusion matrix. And that's going to be a map on our confusion matrix column of the tidy function. Okay, so now we've got a tibble for our confusion matrix, and now we could unnest the tidied confusion matrix. Okay, and we get this set up here. So this is a bit weird in that the cells of the confusion matrix, so cell 1, 1, cell 2, 1, cell 1, 2, and so on. So the cells of the 5x5 confusion matrix have been encoded as name value pairs, right? So if we actually want sort of a square matrix, we'd have to then split this field and then pivot wider in order to get it. So it might be easier to just apply to our original list instead of going via the data frame. Alright, so we could just go grab our predictions, grab our models up here, do our augment, and instead of binding rows, we could then just map our confusion matrix. That might be a better way to go. Yeah, that's a better way to go, isn't it? Okay, so you can see that the neural net is just assigning everything to be building windows, so that is obviously a very poor fit. The others seem to be doing significantly better. Okay, I guess this sort of tidied version might be quite good if you were wanting to do computations on the confusion matrix. So for example, if you had a specific cost function that you wanted to implement, then you could do it by pulling out the right cells, right? So say we wanted to say that an error where you assign a vehicle window to be a building might be worth 10 times the any of the other errors, then you'd want to be picking out the cell 1, 2 and multiplying that by 10, and then taking all of the other off diagonal cells and multiplying them by 1 in order to get the cost of classification. So we could try tuning the models. Right, so we could just maybe have a look at the neural net. Right, where's the neural net? This one here. So let's try neural net 2. We might maybe try only 2 hidden units. Okay, let's check that it converged. Yep, and so we could just do our augment and then evaluate the accuracy. Okay, that's doing no better. Let's try 7 hidden units. Again, that's doing no better. We seem to be doing equally poorly, don't we? Yes. So nothing I'm doing there seems to be helping. Presumably the confusion matrix is, yeah, it's consistently just assigning everything to building windows. So that's not great. What about let's try maybe one more just for fun. No, it's getting the same thing. Okay, what about KNN? So nearest neighbor. Let's try neighbors equals 1. And we could fit. And maybe work out the accuracy and just see if we do better than what we got before. Again, spelling. Okay, let's try 3. Seem to be getting essentially the same thing. Okay. Oh, we actually get better with 10 neighbours. That's interesting. So we're up to 87%, which I think was similar to the forest. Oh no, we actually had 88% before with k equals 5. So KNN and the random forest seem to do best. With k equals, what did I use in the original? 5, was it? Did I not specify? Let's have a look. I didn't specify, so presumably it's defaulting to 5. So it's good to know. You may do better. Okay, so particularly on these small data sets, because we've only got a small number in our training set, small changes could increase that by quite a bit, right? If we just get one more correct, then we're going to boost by a couple of %, right? Okay, so this is a second example, contains information from some images of the Avila Bible, which is a copy of the Bible produced during the 12th century. And this was produced by a number of different copyists or scribes who were transcribing material from other manuscripts into this Avila Bible. And of course they each had subtly different ways of doing their writing. And so we have a bunch of measurements that have been computed off the images. If you want to see some pictures, do a Google search. So we have things like the intercolumn distance, which is distance between columns of text on the page. We've got the upper margin, lower margin, and so on. How much of the column is filled with ink, the number of rows on the page, and so on. So all of these things can help, hopefully, distinguish which of the scribes were used. And this would have initially been done with some clustering, is my guess, because presumably they didn't know which scribe was which originally. And so at some point they would have done some clustering, which we'll cover in week 10, on these different measurement variables from the images, and observations that were similar across those variables would have been grouped together as being a common scribe. And now that we have that information as to which ones we think are common scribes, we can then use that to predict new pages in the text. So the goal is to assign sections of the text, so rows of the text, to the correct scribe. So we have some data here, Avila train and test, right? And so we could just have a quick look at Avila train, and we see we've got all of these different numbers which have all been normalized for us, and then we have the scribe at the end, which has been encoded A through however many we need to get our different scribes. Okay, so we're going to start by, and presumably in the test set, so this is an artificial test set where we also have the scribe, and so the goal is to train up some models with the training set and use that to predict on the test set and see how close we get to the correct predictions. So we're going to start by having a look at some exploratory data analysis. So the very first thing I'm going to do is count the scribe column. Okay, and so what I notice is that the data are imbalanced. Right, so a simple first model would be assigning everything to scribe A. If we did that, we'd get 2,800 of them correct, and out of 7,000, right? So we'd get about a 40% classification rate just by saying everyone is scribe A, which is clearly not the case, right? But that's sort of a baseline model to go from. So. Is a useful, useless model with a baseline. Okay, so hopefully our model should do better than that. Okay, so we'd expect our models might focus on scribe A. Yes, that's the one with the most observations. So it's just something to keep in mind. It may not be a problem, but we'll see when we get to our confusion matrices. Okay, so what about plotting the variables? So what I want to do is start by just looking at each of the variables univariately in terms of the scribe. So I want to basically plot Lomar by scribe and exploit by scribe, right? So these are distributions of numeric measures, right? So to do that all at once, I'm going to do the trick of pivoting longer. Keeping the scribe column out of it. We'll just go with the default values, and then we're just going to chuck it into ggplot, and we'll do perhaps some density plots where x is just going to be the value and y is Y will be known, and then we're going to color by scribe, and wrap then by name. Okay, so things are on different scales, so let's free up the scales. Okay, there we go. Okay, so what I notice is that some are quite good for differentiating. So we've got crills. I can see that the center of the distributions are shifting a bit, and same with exploit. There seem to be some that are very skew, which is odd for normalized data. So I'm wondering whether there might be outliers here. And the one that I noticed immediately is this one here, UpMar. But to a lesser extent, these ones as well. I've got some observations quite out in the extremes of this one. Okay, so some variables seem to be somewhat useful for distinguishing scribes, but also there are potentially some extreme observations, particularly in the variable. Let's look at this more closely. Right. So let's grab our training data and we'll filter it such that the UpMar variable is greater than, say, I don't know, 100. Right, so I'm just basically saying how many observations are bigger than 100. 100 is even probably too extreme. Okay, there's only one bigger than 100, which has UpMar 386, which makes sense. We're going out to 386 here, but I notice also that LowMar is 50, which just seems quite high for a, yeah, so that's way out here. Exploit is normal, I think. Char ratio is 53, which again is extreme. ILS is 83, which is extreme. So this is an observation that is extreme in many regards. So it's likely not representative of the rest of the observations. So we might try we might try just getting rid of it, particularly because there's probably no way that we'd know how to fix this, right? So what would the, what would these numbers supposed to be? Maybe they're 100-fold too big, perhaps. I don't know. We'd be making a guess, wouldn't we? And because there's only one of them, I don't think it's worth playing around. Let's just create a clean version, which is just the training data filtered such that UpMar is less than 100. Right, so let's do that, and then let's plot that. So we'll just do the same plot we had before. And see if that fixes things up. Okay, so that's a lot better. So we fixed this char ratio. Cruel's exploit looks fine. Num rows potentially okay. I'm not sure. Some of the others are still a little bit more extreme, but not hugely. UpMar is we've got a 40 as well. I guess we could look a little bit further. So we should look a little further. And probably also check the test set. right? Because if there's extreme observations in the test set and we getting rid of the extreme ones in the training set, then perhaps we might be biasing things. I guess we could get rid of them in the test set as well, but that means we can't get predictions in the test set. So let's filter. Let's look for UPMAR bigger than 10, say. Okay, so there's 17 of them. And I'm just really looking to see if they've also got, so some of them have reasonably extreme ILS as well. But not really extreme anything else. Okay, here's my 43 here. Again, extreme ILS. Well, this one has extreme weight, so perhaps potentially I could remove this one as well, maybe. Let's try removing less than 40, say, to remove the 43. See if we get something better. Okay. Yeah, I wouldn't want to go much further than that, I think. Because these just could be quite skew distributions. I've got a few observations out here. You see a wee peak there and so on. So I don't want to go too far. I've only filtered out 2 observations. All right, so now I've only got 16 bigger than 10 in the UPMAR variable. Let's just check the test. So UPMAR has some other ones bigger than 10, but they're all sort of in the range that we've already got. So we're probably okay. So let's fit a range of classification models. Okay, so we might try, we might try KNN. Obviously we're going to not use a logistic regression. That doesn't make any sense, right? Because we've got 12 variables, we've got 12 different classes here. Something like that anyway. Yes, 12. But we could try nearest neighbor. Maybe with 5 neighbors. We could try a tree. We could try a neural net. Maybe with 5 hidden units, we'll give it a bunch of epochs to work through. We try random forest. I guess we could do multinomial regression. We could do LDA. KDA, I guess the problem with KDA is we can only use 3 variables. Okay. And so if we've only got 3 variables we can use, it's like which ones should we use? I guess we could look at this and try and pick 3 out, like maybe we'd use these first 3 perhaps. Or as a way to do it. The other thing that we could do is we could try some feature reduction. So we could try something like running a principal components analysis on these 10 columns. So those of you who take 161323 multivariate analysis would come across that method, and it's just basically a way of summarizing those 10 dimensions into fewer. So say 3 dimensions. And the idea is that once that summary is done, you will have lost some information because you've thrown out information from some of the information. Because we've gone from 10 dimensions down to 3. But now we can utilize KDA. And hopefully those 3 dimensions will capture a reasonable amount of the variation in the data. So that's something that you could try if you know how to do that. If you don't worry about it. No big deal. We'll Google it, right? There's numerous tutorials on how to do that. So we can't really try KDA, although maybe we just want to do it anyway with maybe those first 3. I guess that's going to be a problem for the fit though, isn't it? So let's not do KDA. Keep it simple. We could try naive Bayes. Right, and I think we use the naive Bayes engine, don't we? Okay, and then with each of the models, we're going to fit them. So it's going to be scribe in terms of everything else. And our data is the evala.train.clean. All right, so that's our fitted models. We haven't loaded the scrim. Okay. So there's our model fits. It's having trouble with naive Bayes. So what might be wrong there? I think I've got the engine wrong, haven't I? Let's try that. The only trouble of doing everything in a list is that any errors that are spat out, you've kind of got to dig down a little bit before you find them. Okay, we've got no errors now, so that's going fine. So these are fits. Now we could take our fits and augment with our test data. Okay, and then we could evaluate the performance. So we could take our PRIDs and we could bind them up together, group by the model, and then compute the accuracy. Okay, so here we go. So we get, okay, so the random forest is by far doing the best by a huge amount. It's really massively in front, isn't it, of the others? So at this point, I mean, I haven't done any tuning or anything like that, but to be honest, I doubt tuning is going to take a model that's performing at only 73% up to one that's performing at 93%. So my guess here is that if I'm wanting to tune, I would probably just focus on the random forest at this point and probably not bother with anything else. Let's have a look at the confusion matrices. So I want to map confusion matrix. Just to see what they look like. So yeah, you can see that that a bunch of them are assigning a whole heap to be Class A because it's the most dominant one. But it's also getting quite a few of Class A1. I guess that's just a numbers thing though, isn't it? You can see the random forest is just doing incredibly well. LDA is doing poorly. Naive Bayes isn't doing great either. But yeah, I'm thinking that, looking at the output from the random forest, there's potentially a class imbalance issue in that, there's what, maybe 60 odd observations here that we're assigning to A when we don't have to. But it's not a massive class imbalance issue really. So I'd be quite happy with that. I might try, potentially we could try tuning it, we could try changing the, the number of predictors it chooses for each split, and see if that makes any difference. But I think we'll just go with the random forest. Okay, and then this last question is an interesting one. So if instead of classification performance, the goal was to understand how the scribes differ, which model would we prefer? So clearly the random forest is doing the best in terms of determining which scribe is which. But the problem with the random forest is that it's a bit opaque as to why it's making the decisions that it's making. So you can do something, so you can get things like variable importance scores out of the random forest, which tells you which variables are useful for classification, but that doesn't tell you how the scribes differ on those variables. I guess we could go back to the original data, so our plots, and we could say something about how the scribes differ in terms of perhaps the exploit here, or the char ratio and accruals and so on. Or we could try doing plots of perhaps these two against each other, like a scatter plot, and to see whether we can take advantage of some correlation. So we could try that. But generally the forest isn't that useful for telling us why things are happening. So the forest is definitely best for overall accuracy and prediction performance, but is a bit opaque in terms of how the different scribes differ. Instead, if we want to know we really have an inference problem. All right, so this is more sort of classical statistics rather than prediction. So our goal isn't necessarily excellent separation of the scribe. Instead, it's determining why the scribes differ and how they differ. And so we want a model that's explainable. So multinomial regression would be 1 because it gives us the regression coefficients, and they may be able to tell us something about how things differ. Or it might be LDA, which tells us how the group means differ. or a tree. Okay, i.e. it's the simpler models that are useful in this case. Right? It's because we're answering a different question. So for example, we might want to grab our LDA stuff. So we fit an LDA, didn't we? Yep. So we might want to grab our fits. And we might want to pull out the LDA object. And to pull out things from a list, you can either use two square brackets with the thing that you want to look for, which is either by index or by object name, or you can also use, which is perhaps easier, fits.lda, or you can use pluck. Right, all of those are equivalent. Okay, and so then we want to grab the underlying fit object. This is what pluck is useful for. Okay, so there's the fit object, and so now you can see the group means. Right, so if you just sort of look down this ICD column, scribe W is the one with the most negative ICD, whereas scribe I is the one with the most positive ICD. So ICD helps you distinguish I and W, for example, whereas B is distinguished by a high upmar. Right, and so because the LDA model is simple, it is explainable. And we could also have a look at a tree, right? So we could pull out our tree fit and plot the tree. My guess is that that's still going to give you something that's quite complicated. Perhaps we'll try it. So what was it? High upmar. So we could take our fits and we could pull out our tree and our fit engine from the tree, and then and then we could do a usual plot tree mod. And text. Let's have a look at that. Okay, that's perhaps a tree that's a little bit too simple. So we can see that really we're only distinguishing A, F, E. Yeah, so we're not distinguishing all observations here, are we? I don't think. So there's no B, C, or D, which is perhaps why this tree wasn't doing any good. So we might want to use a big one, but based on this, you can see that if the number of rows is larger than 0.84, then you more likely be scribe I. So scribe I is associated with high number of rows. Scribe X is associated with a large number of peaks. Okay, and so on and so forth, right? So typically the idea is that if you want to explain what is going on, you need to use a simpler model. That's a different prospect from being able to get good predictions. So good predictions may need an opaque model. So if you imagine, the forest has 500 of these trees, right? And each one of them is deliberately different, right? The forest is designed in a way that ensures that the trees are all different. So each of those decision trees are telling you different ways to make the same decision. right? So it's very hard to summarize that information. So if we're wanting to summarize why things are as they are, you need to use a model that is simple as a consequence.